Good, good. Everybody can hear me back there? Okay, I think this mic is live too, so hopefully I don't go in feedback mode. Thank you so much. I want to thank the organizers for having me. Throw back on Kevin and Jacob couldn't make it, but this has been an awesome day. Seriously, I love having a group of bioinspired roboticists and folks interested in sort of understanding principles of biological systems. And that's kind of where I want to start my talk off with. I just want to step back and kind of give my perspective on what I think are the pillars of bioinspired robotics. The first one is the most obvious answer, which is locomotion. That we like to study things that move because animals, cells, almost everything in biology in the natural world moves in some form or fashion. And I think movement is a fundamental component of bioinspired robotics and of systems that embody bioinspiration. The second one is adaptation and learning. Animals and robots have to react to changes in the environment, in their own body, over the span of lifespans or milliseconds, and starting to understand how adaptation and learning can be embedded in bioinspired systems, I think is really important. Another one is forceful and confined interactions with the world. We generate force through muscle. Muscle produces forces that allow us to push on things. And so understanding how the interaction between bodies that exert forces against the world and then move via those forces against the world, I think is a fundamental part of bioinspired robotics that is sort of relevant through the direct drive robotics applications in Lego robotics and soft robotics and these other kind of trends that I think we see more recently. There's one element that I think is a hallmark to all of bioinspired robotics that I didn't put up here, but that's oscillations. And that's going to be the fundamental goal of my talk today, is to talk about systems that oscillate and how we generate useful oscillations for locomotion and for adaptive behaviors. All of these large animals move through oscillations. We don't have rotary joints, so we can't just continuously rotate. We flat back and forth or oscillate back and forth. And I want to talk today about kind of two broad stories of adaptive bioinspired oscillations in robotics. So this talk is kind of broken up into two halves. And the folks who've done all this work are sitting in the audience and will be able to tell you much about this work, as I'll sort of guide you to a little bit later on with this James and Wei. And so from the theme of sort of principles in biology as leading towards bioinspired robotics, I want to talk briefly about two methods that biological systems use to generate oscillations. This is a fantastic review down here that I would highlight everybody today to look at by ICRA. And it's fundamentally talking about rhythmic motion in biology. And they kind of categorize two different ways generally that living systems generate rhythmic movement. The first is through a series of network of cells called a center pattern generator that generates basically a rhythmic output that then is fed out to limbs, to other body elements that effectively governs the timing between phases of oscillatory motion across all these different appendages or degrees of freedom. But ultimately, this center pattern generator is sort of thought of as a clock for the system that is undergoing maybe slow feedback through sensory processes. Okay, so you have a kind of underlying clock that is generating a signal going out to the appendages, and it's somewhat analogous to kind of time-dependent forcing of the system. You're just putting out, sine omega t to all of your joints, and they're oscillating in accordance with that. And the counterpoint to that is what they call reflex chains, where a reflex chain is basically just a very low-level network of motor neurons and sensory neurons that are innervated in such a way that they generate rhythmic oscillations, but they're rhythmic oscillations that are adaptive and are undergoing instantaneous feedback from the environment and the appendage that they're driving. So you can think of this as sort of limit cycle systems that are undergoing nonlinear oscillations that are adaptive in that they can change frequency. If you are, say, little C. elegans worm that's swimming in water, and all of a sudden you're crawling on land, and now the forces on your body have changed by a factor of 10,000, and the reflex chain can respond to that kind of change in external forces by generating different rhythmic oscillations based on that kind of low-level feedback between motor neurons and sensory neurons. And again, these are kind of analogous to limit cycle oscillations, right? And so you have non-autonomous oscillations and autonomous oscillations, if you want to think about it that way. broadly, and I should say everything I'm going to show you is basically the things that you would learn in the first class of nonlinear dynamics that I myself am not developing, but we're incorporating into I think novel uses for robotics. A kind of the most basic classification of oscillatory motion generation comes from looking at your system as a dynamical system and then mapping it onto some phase oscillator type coordinate system. If you look at an oscillator in a phase plane, the limit cycle of that oscillator might look something like some circular limit cycle, where I can describe the state of the system via some phase angle that will be continuously rotating and some radius of that point, the state of the dynamical system. And so I want to kind of classify a couple different types of oscillatory motion generators. And this is very much a non-rigorous way of classifying these oscillatory motion generation. But I first want to call just feed-forward oscillators. This is just that example of the central pattern generators that I showed you before, where you have just a phase that is just constantly increasing in time, and that there's no feedback affecting that phase. So you just have your sine omega t that is going out to all your joints, and you're just oscillating according to sine omega t, independent of whatever external forces are acting on you. Now we can increase the complexity of it a little bit by allowing for a feedback oscillator, where now instead of just having your phase of your system, the phase of oscillations increasing linearly in time, you have some feedback function that can take information from the body and from appendages and speed up or slow down those oscillations. Lastly, what I want to call are embodied oscillators, and these are truly just nonlinear oscillators that are generating motion through low-level feedback. We call it proprioceptive feedback here, which is just sensing of your own state variables and then oscillating according to those state variables. So say a motor that just takes input of position and velocity and executes oscillations based on just those position and velocity. Specifically, there's no explicit phase that you're tracking or that you're integrating. It's just you're undergoing oscillations based off of this system here. And so these systems allow for adaptive oscillations. Adaptive meaning that they can adapt to environmental interactions or changes in body type. So I want to get back to the story of the two different types of adaptive bioinspired oscillations in robotics. The first one is called the adaptive wing beat of insects and robots. And this is, you can see James's presentation tomorrow in the Bioinspired Biomedical Systems section. You can take a look at this paper and you can take a look at this poster tomorrow. This is a collaboration with insect flight biologists as well as James and myself from my lab, where we've sort of categorized the dynamics of a flapping wing insect or a flapping wing robot as a very simple spring mass dynamic system. But we wanted to focus on the actuation side of this system. And from the biology, we know that there's basically two ways that flapping wing systems generate oscillations, flapping wing insects specifically. There are synchronous insects that generate an oscillatory motion of their wing according to a direct activation of the muscle that drives that wing. So you've got a one-to-one activation of the muscle that is causing the wing to oscillate. And these are called synchronous insects. And some good examples of these are like moths and butterflies and locusts. But as insect flight evolved and as insects got smaller and wing beats needed to get faster and faster, insects evolved a new way to generate oscillations, which are called asynchronous oscillations. And these asynchronous oscillations use a specific property of the muscle called delayed stretch activation, such that wing beats are generated in the absence of any neural intervention from the motor system whatsoever. It's just a property of the muscle that has a specific delayed stretch activation that causes oscillations without there needing to be any sort of signals coming from the brain from lower level neural centers. But nobody's really categorized or written down a dynamics equation for asynchronous actuation. And furthermore, can asynchronous actuation be useful in the context of robot flight? And this is what we wanted to tackle in this paper that, again, James will be able to tell you much more about. And so the first thing that we did was basically looked at, with our LID colleagues, what the response of these delayed stretch activated muscles are. People have done lots of these stretch hold responses of delayed stretch activated muscle. And what you see is that basically when you stretch the muscle, there's a sort of delayed rise in the tension, the force that the muscle pulls back on with. And we kind of recast this as basically just a step response of a dynamical system, which allowed us to write down a representation of asynchronous oscillations. Namely this one down here. And this allowed us to connect together the spring mass dynamics equations that just define a flapping wing system with the delayed stretch activation muscle dynamics that are present in the muscle itself. And the flapping of these systems is just undergoing this sort of self-excited feedback from just the muscles being stretched by the inertia and the elasticity of the spring mass damper system, and that just feeds back on itself. I'll allow James to tell you that the system produces stable limit cycle oscillations and all of the fun analysis that he's done of these systems. But I want to just focus on how this asynchrony can help flapping robots. There's kind of two areas, these two areas that we think are useful are, one, responses to physical change. Insects, their wings collide with obstacles all the time. If you've ever heard a bumblebee up close when it's sort of flying around flowers, you'll hear the wings colliding with foliage at hundreds of times per second. And the way that biologists tell how old an insect is, they just look at their wings and they look at how tattered they are. In the second case, we think that this kind of low-level excitation of wing beat dynamics can help with interactions with the environment. There's a little tripwire here that I'll show you this video again. You'll have to focus on that this honeybee is able to stop their wing beats within about 2 wing beats just by colliding. To study this system, we built a larger scale version of a flapping wing system. And critically, we added in an elastic component to this, as well as a motor that we have torque control over, and a wing embedded in water in a dynamically scaled context, so that the Reynolds number is still approximately that of these flapping wing insects that we're interested in. And we wanted to kind of ask, how do the system dynamics of this delayed stretch activation behave in these different, these two different scenarios that I just showed you? One where the body is changing either through, say, wing beat degradation or changes in body mass or something like that. And the second one being when there are collisions or interactions with the environment. So the first case was we just set up oscillations of our system. Set up meaning we turned it on and gave it a little flick and let it go unstable, and now it's oscillating as a limit cycle wing beat. And then we just added or we changed the mass of the system by dropping a little inertia plate on it. When you add this mass on, there's this sort of transient time where the system adapts, and then you see, in this case, larger wing beat amplitude and slower wing beat frequency. And we can track the change in wing beat amplitude and frequency across the change in inertia. You can easily just recast this as change in wing beat inertia versus 1 over frequency squared, the emergent frequency squared. And you see a linear relationship, just indicating that the system's just adapting to its new resonant frequency. All this is very, very simple, except that it sort of comes out very nicely just from this low-level way that we're driving these wing beat oscillations. The system automatically adapts to its resonant frequency. And this has actually been seen in the 1960s when people clipped wings of these asynchronous insects and showed that they changed their wing beat frequency in response to changing wing inertia. So we think this is kind of cool and allows for like rapid adaptation of these flapping wing robots to kind of changing body mechanics. And then in the second example, I was motivated here. There's a little tripwire here. You see this wing is going to collide with this tripwire in just a second, right there. And the wing beat frequency of this honeybee is 180 hertz, right? So it stops this wing beat in about 2 to 3 wing beats, and then it starts it up again immediately. I think that's pretty impressive. I mean, again, like I'll play this again at 180 hertz, you can sort of sensing intermittent contact with the obstacle and then halting the move. And we propose that basically this is just a byproduct of having this delayed stretch activation as the thing that is generating the oscillations. We wanted to demonstrate this by basically just making our robo flapper collide with an obstacle and see what happens. So James again set up his experiment, and then at a certain time applied a perturbation to the wing, just hit an obstacle. The wing beat is halted, and then all of a sudden, with a little kick, you can start up wing beats again. So we think that this kind of asynchronous actuation gives you nice adaptive responsive behaviors of these flapping wing systems to allow them to adapt to, I've said it a million times, but adapt to changing environments and interactions with the environment. To give myself enough time, I'm going to move on, and I want to talk about one other topic that is very much related to this, which is synchronization through contact. This all came about from observations of these worms, C. elegans, that when they get into large clusters will synchronize their swimming gaits. And some biologists asked the question, are they sensing touch from other worms or sensing chemical cues that cause them to synchronize? So they went in and they basically silenced all of the sensory neurons in the worm's body so that they can't sense touch, they can't sense other worms being near them, and they still synchronize. And what they posed was that it's this term, steric hindrance. It just means the fact that you have a solid body that can't pass through another solid body. It's just contact. The fact that these worms make contact with each other, and the fact that their neuromuscular system is driven, these oscillations are driven through these local feedback responses of body segments that sense local bending of their body, and then they create muscle contractions. These two things may lead to synchronization just without any sort of communication of these groups. And we kind of wanted to ask the question, what are the dynamical principles for this kind of synchronization? And could we use this for interesting robots that can synchronize implicitly without having to communicate at all? I did my PhD in a physics department, so we stripped all of the details of things away. I'm sorry, and we performed this illustrative study. We said, here's a worm. Okay, kind of looks like a worm, right? Here's another worm. Kind of looks like a worm. These are two just joints on two independent robots that are going to just oscillate according to proprioceptive, so just local feedback laws that cause them to oscillate back and forth. It's just a weakly nonlinear oscillator. But we're going to allow them to make contact with each other. We're going to ask the question, do these ultimately synchronize their gaits? Do they form antiphase synchronization? Do they just kind of constantly clack together in some sort of chaotic manner? And so this is the output of one of these experiments. I'll show you this in a second here. So each of these motors is just undergoing oscillations according to a simple nonlinear oscillator feedback law. But they're able to make contact with each other. And by making contact with each other, they can adjust the phase of each other. We set up the experiment, we move them to some random initial position, which causes them to have random phases. We then bring slowly one of the oscillators into contact with the other one. And if you hear this, you hear the annoying sound that's going on thousands of times in the loud. And they ultimately synchronize. This happens every single time they synchronize, they synchronize, they synchronize. I invite you to take a look at the paper we published last summer. There's lots and lots of gory details of why this happens, and show very simply that this will always be the byproduct of contact between these kinds of nonlinear oscillators. And here's just one example of that. This is looking at the phase difference from contact n to the phase difference at contact n plus 1. So it's just a return map looking at the sort of iterated mapping of contacts. And what you see here is that this crosses the one-tone line, meaning that there's a stable fixed point here in sync where there's no phase difference between the two oscillators. And critically, this is all data here. This black line is this function that we derived that has no fit parameters in it whatsoever, just the coefficient of restitution of the balls, which we've measured. Okay, so this does a pretty darn good job of just modeling these systems as phase oscillators that undergo these kind of hybrid collisional interactions. So again, I showed you my sort of robotic worms. We thought that those were enough to kind of give us confidence that really what's going on with these sinking swimming worms is that they are activating their body oscillations according to local feedback rules. Those local feedback rules, when coming into contact with other worms, cause them to update their oscillatory state. And what happens is you eventually get synchronization of the group. So the question is this useful for actual mobile robot groups? The first way that we just addressed this was in simulation. And we just set up basically a simulation where we compressed a bunch of these 3-link swimmers into a very narrow gap. And they're all being driven in a time-dependent manner here, a non-autonomous manner. They all have different phases, so there's large contact forces between them. At time 200 seconds, we turn on the limit cycle actuation, and they're all going to immediately synchronize their gaits according to the same things that we showed with the single robot joints and with the examples from worms, right? So the synchronization of joints can cause a minimizing of the contact forces among the robots, and it happens extremely quickly. We actually moved now to real robots. They're real 3-link robots, okay, so they're still relatively simplistic. And we started to play around with the different, what we call proprioceptive feedback functions that you can put in the system. Proprioceptive feedback just means, again, that I'm oscillating joint, but I've got some internal representation of phase, and I'm comparing my oscillatory phase of the actual physical system with the sort of underlying phase that I'm thinking my system is oscillating at. And we put in functions that allow you to adapt your phase. And we study these with different amounts of, let's say, proprioceptive gain. What you're going to see here are 4 linked swimmers. This has negative proprioceptive feedback, so they don't synchronize. When the proprioceptive feedback is optimal, these systems synchronize incredibly quickly. And when it's larger than a certain value, they don't synchronize at all. All of these values are chosen based off of some very nice theory that we worked out according to these just simple kind of oscillator rules with contact. And this allowed us to make simple snake-like robots that we challenge to squirm, slither through a narrow channel. They start off with different oscillator phases. Again, there's no communication happening between these at all. They're just responding to all of the contact that they're experiencing in the world. But the only contact that has any sort of phase associated with it is the contact from a neighbor. Those 2 neighbors adjust each other's phase accordingly, so that you ultimately get synchronization of them as they're moving through the so this is pretty cool. We can actually set up these kind of synchronizing groups based off of very simple phase feedback rules and very simple adaptive oscillations that we set up as our generator of locomotion. I want to show one more cool example of this. We wanted to try different kinds of modes of interaction in these groups. And so kind of inspired by the collective manipulation that we see from ants. Roboticist Mark Karkowski and others have looked at their little micro tugs and how they can work collectively, and just our kind of common knowledge about how much we can collectively push objects when we push together. We wanted to look at systems that might be able to synchronize through manipulation of a common object. So we built these very simple, simple walkers that just have a single leg. This leg is actuated via torque that is generated from a phase equation. And what I want to show you here is first on the top here, there's no object. And so these robots are going to start off completely 180 degrees out of phase. You see this is the leg angle that we're plotting here, robot 1, robot 2, and they just evolve and they stay out of phase during the walking cycle. If I put an object in front of them, what you're going to see is that incredibly quickly they're going to synchronize their walking. Again, there's no communication. This is just the physics of synchronization, the physics found in your oscillators. But they synchronize up and they're able to actually push heavier objects once they've synced. Here's a case with 4 robots. They're all starting here. We just show the phase down here. This is just representing the phase angle as it evolves. And incredibly quickly, they synchronize their gaits. They're able to all push together. This is super cool. And again, it's just coming from very simple physics that we're building. You can do this. We weren't able to build 100 of these, but if somebody wants to fund this research, please. But we can do this in simulation. We could set up 100 of these robots, all undergoing their own activation to get local proprioceptive feedback rules without communication. And here's just another example of varying what we call this proprioceptive feedback gain. In the case when it's negative, they don't synchronize. They actually want to turn it into antiphase synchrony. In the case that it's optimal, they push this object the furthest in the same amount of time. They're overstimulated, they don't move at all. So here we are. I think these are two cool, completely unconnected, at least from an organismal perspective, stories about adaptive oscillation with bioinspired robotics that come from really trying to understand how we can drive these systems through adaptive oscillations and what the beneficial features might be from these. I want to say that adaptive oscillators are, I think, really interesting, provide a lot of cool properties. Not new at all, I'm sorry to say. And there was a flurry of activity from ICRA people in the 2000s. And lastly, I want to say thank you, everybody. And thank you to James and Wei specifically. Please find James tomorrow at his workshop and find Wei at his poster this afternoon. Happy to take any questions. Sorry if I didn't.
No, you did it. Thank you.
Thanks for the nice presentation. I have a question on the experiment where you compress the environment and you show that you start synchronizing. In that experiment, you do not have a shared media like a fluid. And so the question is, if you add that, wouldn't they start synchronizing much earlier than help using a proton?
Absolutely, yes.
Can I ask you another question?
Sure. The answer is yes. Yes.
So the other question is about the proprioceptive feedback, how it's actually implemented in the lab.
Great question. Okay, so yes, fluidic synchronization. Again, synchronization is nothing new. There's thousands of papers on it, and lots of animals, cilia, things like that, synchronized through fluid. The proprioceptive feedback, it's a Van der Waals oscillator that is in its weakly nonlinear state. Okay? So it's not the kind of relaxation oscillator that you see from Van der Waals typically. It's just got a pretty much harmonic, like sinusoidal output. The equations, you can look it up in the paper, but it's basically just a 3-term equation. So we're just watching position, or we're watching velocity, and we're just generating torque based off of both of those things.
So, but for the first question here, so you would expect the synchronization to happen even at large distances, and without context.
Yeah, I mean, it's sort of a scale-dependent question, right? I think that
for the actual flight, so if they are close enough and there is some aerodynamic effects, would you expect?
Well, and again, I think it's a scale-dependent question. I think it depends on Reynolds number. And I think it depends on specific type of interaction. Yes, there are lots of examples of fluid-mediated synchronization. Yeah, thank you. Anybody from the chat?
Although we can see. Oh, maybe. Somebody just turned their camera off. No.
I had a question actually, if you can hear me.
Yes. We can, yeah.
Sorry, it's very dark because it's night here. But I noticed in the phase diagrams you had a bit of a span just at the end when you had the synchronization of the agents. Is that span a kind of ripple effect, or is that just natural variance? Or is there kind of an ordering when you have the 100 from, say, the first one to the 100th?
Oh, span. Sorry. Yes. Whether they exactly synchronize to the same phase, or whether there's some phase variance that's allowable. That's a good question. We haven't done a systematic study on that. The thing I should say here too, which is not usually done in the studies of synchronization, is that they all have an identical frequency, like underlying frequency. Typically, when you see studies of synchronization, I think the most wonderful phenomenon is when you have entities that have slightly different underlying frequencies that still all lock to the same frequency. So we haven't actually done that with these. We've done it in the collisional case, and they do phase lock, or frequency lock as well as phase lock. But yeah, it's a good question. I don't know the answer though, whether they'll converge all to 0, or if there's some constant and persistent non-zero variance of frequency curves.
Because I was wondering, for example, when you had the 100 of them in the simulation, it looked like there might have been. I was wondering if there was a kind of ripple from the first one to the end, or if that kind of segment was caused just because.
No, it's a good question. I don't think there's any spatial dynamics there. Like I don't think the one next to the other one knows anything different than from the 100th one that far away. They're all interacting through a common object. I think we have a question in person too. Did you have a question?
Yeah. Is this like mathematically proven? Like, is there some kind of estimate? Because you showed some equations. Can you prove that they converge this way, or because you showed a lot of empirical, you said a bunch of papers that were empirical, but I don't know. It sounds like it could, if it follows the dynamics of these equations, you should be able to prove it. But
yeah, and that's kind of what this was originally. I think a 75 slide talk that I had to whittle down to 40. Sorry, I'm kind of joking a little bit, but let me just find the one plot I just want to show you. And as soon as you guys pull me off, there's somebody.
After this question, this is the last question.
But this plot right here, so there's a much larger expression for the return map that we derive that is not present in theory beforehand. It just comes from basically treating 2 circular limit cycle oscillators via a collision, just an inelastic collision, and you can basically fully work out the return map. And that's what I'm saying. This black curve that's on this data here is not a fit. It's actually the thing that's coming from the theory equation right there with a measured coefficient of restitution of the walls. That's the only parameter that comes into it. So the fact that like it overlays the data, I thought was already pretty cool, irrespective of not having to have any fit parameters in there. So that gave us pretty good confidence that that we're modeling the system relatively well.
Okay. Thank you so much.
Thank you, everybody.
Next is the poster section, and then some questions. Very cool. stuff.